As we begin to enter into a discussion on molecular orbital theory, it's important that we begin to expand the knowledge that we would have learned about in general chemistry or organic chemistry. Importantly, a molecular orbital is actually a linear combination of atomic orbitals. And that just means that you add them together. So if you have n number of atomic orbitals, that you should also have n number of molecular orbitals. So an s orbital plus another s orbital becomes a sigma orbital. You see what I mean here? In addition to that, anytime you create a bonding molecular orbital, you should also generate an anti-bonding molecular orbital. So for that reason, when we take our 1s orbital and combine it with another 1s orbital, this generates two new orbitals because we started with two atomic orbitals. And that's what linear combination of atomic orbitals means. It's also important that we understand the geometric shape and the symmetry involved in making molecular orbitals. For example, you will have seen previously that an s orbital plus another s orbital can combine to form what's called a sigma orbital. Okay? And when they combine, what that sigma orbital looks like is if those two had fused together. Okay, so it's a linear combination. So if you had added them together, this is basically what you would get. And in essence, this happens because they overlap. So if they come close enough together and there's an electron in each of them, they can combine to make our sigma orbital. Now, importantly, we call this a sigma for a particular reason, and it has to do with symmetry. Okay, so previously you would have learned that the first bond formed in a covalent bond is a sigma bond, and then any subsequent, like second, third, double, or triple bond is going to be a pi bond. But the real reason that we call them sigma and pi bonds has to do with this thing called symmetry. So if you notice, so if we had two atoms, and let's just assume that these were just two hydrogen atoms, here is what the s orbitals could look like, and they would combine to form our sigma bonding orbital and also our sigma anti-bonding orbital. So the anti-bonding orbital would be in the case where you had one which was shaded or in a certain phase and another which was unshaded or in a different phase. So positive or negative when you solve a wave function. And what this ends up looking like, since they are not in the same phase, they cannot have constructive overlap. So instead, they have deconstructive overlap, where they actually separate because they're out of phase with one another, and they create the sigma anti-bonding orbital. All right? So stay with me. So here we have a sigma bonding molecular orbital and a sigma star anti-bonding orbital. Again, both of them are sigma due to their symmetry. Now, what does that mean? So if you had these two hydrogen atoms combined to form an H2 molecule, this is what we call the internuclear axis. So the internuclear axis is the axis between those two atoms. And notice that's because, we can rotate this molecule. If we were to rotate along this internuclear axis, there would never be a point where along that internuclear axis there would be a node, or a location where you are unlikely to find an electron, or a zero sum for solving the wave function. Okay, that's what we call a node. And a common example of this is, you can think of a p orbital, which has a node at the center of the atom, whereas s orbitals, being spherical, don't have that. So now, notice that if we were to rotate along this internuclear axis between these two atoms, there would never be a case where the phases would flip, and in addition, you would never find a node along that internuclear axis. That is actually why we call it sigma, and that has to do with rotation along the internuclear axis, never producing a node or a phase change. Similarly, even though this is an anti-bonding orbital, along that internuclear axis, if we were to rotate it, what would happen is that all of the phases would remain the same, and all of the density is still along that internuclear axis. Yes, there is a perpendicular node. However, along this internuclear axis, there's never a point where a node would be present when you rotated it, based on the location of the sigma star anti-bonding orbital. Now consider the difference. So if we had two p orbitals, which I'll go ahead and draw in the phasing, if we had two p orbitals, these could combine above and below the internuclear axis, and if we were to add those two together, because remember we're making a pi molecular orbital, which is a linear combination of atomic orbitals, what that would generate is something that looks like this, where you have all of the orbital density above and below the bond axis. Okay, and we call that a pi bond. All right, and we call it a pi bond because if you notice, if we were to consider the internuclear axis between two atoms, doesn't matter what they are, obviously it's not H2 because those don't have p orbitals, but along that internuclear axis, if we were to rotate it, there is a node all the way along that internuclear axis. In addition, if we were to rotate it, this shaded in phase would go to where the unshaded phase is. And that is the reason that we call this a pi bond, because it has pi symmetry. Similarly, we can consider the interaction between, for example, a p orbital and a d orbital. So if we were to place the shading like this, notice that you have this internuclear axis, and along it we can combine, because of the phase match, these two lobes present in the d orbital and the p orbital. And this would create also a pi bond, which looks like this. And that would be our new pi bond that's formed. And again, we call it a pi bond because if you were to rotate along the internuclear axis, there are two lobes that combine to form this new pi molecular orbital. And if you were to rotate it, the phases would switch. And because the phase switches, if you rotate along that internuclear axis, and there's a node along the internuclear axis, that is actually the reason why we call it a pi bond. It has nothing to do with being the first, second, third, or fourth bond formed between two atoms. It has everything to do with that symmetry and that rotation along that internuclear axis. The graph you just saw on the screen depicted the relative energies, or the effective nuclear charge, of different atomic orbitals for different elements on the periodic table. I'm going to bring it up again, and I want you to pay attention to the difference in energy between the s and the p orbitals of nitrogen and oxygen. Again, you're looking at the difference in energy between the s and p orbitals on nitrogen and oxygen. In a previous video, we drew the molecular orbital diagram for nitrogen, the diatomic molecule nitrogen, or N2. And if you look at the energy diagram depicting the atomic orbitals, the linear combination of atomic orbitals known as the molecular orbitals, it looked like this. And importantly, because the energy between the s and the p orbitals are less than about 13 electron volts, the s orbital and the p orbital with the same sigma symmetry can mix. We called that sp mixing. And what that did was pushed up the sigma bond that's formed, the second sigma bond that's formed above these pi bonds. Okay, and that was because these s and the pz orbital were close enough in energy to do sp mixing. Okay, importantly, if you notice on that graph that I just showed, the s orbital and the p orbital on oxygen are greater than 13 electron volts in distance from one another. Now what this means is that the s orbitals lie lower in energy, and so much so that even though the s and the pz orbital have the right symmetry to mix, they cannot because they do not have the same energy. So importantly, it's not just about the symmetry of the atomic orbitals that can combine to form molecular orbitals, but also whether or not the energy can sufficiently to allow for this overlap to occur. Now in your quantum mechanics class, you will have solved the wave function for the overlap to figure out exactly how much overlap exists between two atomic orbitals, but in our class we're going to focus more on a qualitative approach. So now let's walk through for an oxygen, or O2, and see how that manifests on an energy diagram. Okay? So in this case, I see that the 2s orbital on nitrogen is here. However, due to the strong effective nuclear charge of oxygen, the s orbitals lie a little bit lower in energy. Okay, so I will place those two s orbitals, and again, remember we only focus on the valence shell of orbitals when creating our molecular orbital diagrams. So the valence shell of orbitals in the case of oxygen is going to be the 2s and the 2p orbitals. And I'm drawing these basically at the same energy because they're both the same atoms. Importantly, as we move on to heteronuclear molecules, these may not always be at the same level, and we need to start to think about how that is going to manifest in our molecular orbital diagram. Okay, so oxygen has 6 valence electrons, so I'll place those in as well. And as I go through here, I'm also going to consider not just the energies, but the symmetry when creating this molecular orbital diagram. So we have already seen that two s orbitals can combine to form a sigma bond. The s and p, the two s orbitals that are out of phase with one another create our sigma antibonding orbital, or sigma star. So that is what happens here with these two s orbitals. And remember that these s orbitals cannot mix with these p orbitals. And again, that comes from the distance between the s and the p orbitals on that chart that I showed depicting the relative energy or the effective nuclear charge. So because of that, we don't have s contributing anymore to the next sigma bond that's formed. So the next sigma bond that's formed is going to be between two pz orbitals. Notice that when these two pz orbitals are pointing towards one another along the internuclear axis, that if you were to rotate around that internuclear axis, even though there's a node here, however, when you rotate along that internuclear axis, you're not actually flipping the phases. So because of that, this forms a sigma orbital that if you were to draw it, you would see the overlap occurs along the center. And this would be our next sigma bond that's formed. Okay, so these linear combination of atomic orbitals make this sigma bond. So, therefore, because there's such a high degree of overlap, meaning there's relatively few nodes along the internuclear axis, that this overlap is going to push this very low down in energy, or it's going to cause it to be far more stabilized. Notice that it does drop down below because there is no sp mixing, which is compared to N2, where we did have sp mixing, it actually pushed it up or destabilized that molecular orbital a little bit. So now we've got our sigma star, and this new sigma bond that's formed. Obviously, if we had two of these pz orbitals that were combining out of phase with one another, that is what produces our sigma antibonding orbital, which would look like this. We would have a node in the center, and this, if we were to rotate along the internuclear axis, we notice that the phases don't flip. So again, this is a sigma symmetric orbital, but it is an antibonding orbital because the orbitals are not in phase with one another. Another important distinction that I haven't really mentioned yet is that the stabilization that occurs between orbitals is manifested by how well they overlap. Similarly, the amount of destabilization of the antibonding orbitals, number one, is always greater than the stabilizing energy between making a bonding molecular orbital, which is why I drew this a little bit, it's lower in energy for sure, but the degree to which that the antibonding orbital goes up in energy is greater. So just keep that in mind. So basically, just to really drive home that point so you don't get confused, is that if you were to consider this energy as E2, and this energy stabilization as E1 between the bonding molecular orbital where the original atomic orbital began, then E2 is greater than E1 in absolute terms. Just something to keep in mind. All right, so now we have our px and our py orbitals, which can align along the internuclear axis, again above and below, to create our pi bonds. And the py orbital would be the one going in and out of the board, which would just look like this, just rotated towards you. So that creates our new pi bond, which again looks like this, where you have all of the orbital density above and below the internuclear axis. So that is our pi bond as a result of a combination of these two atomic orbitals. And then similarly, our antibonding orbital would be the one where they're out of phase with one another. And this would create our antibonding molecular orbital. And I'm actually going to jut it out a little bit because when they're out of phase, that actually is such a destabilizing force that it causes them to kind of push away and be repulsed or repelled by one another. All right, so that is our pi star, and that's what that looks like. So now I'm going to draw my new 2 pi bonds from my py and my px orbital. And here will be my pi antibonding orbital. So this is pi, and these are pi star. And now I need to go through and add the rest of my electrons. And importantly, just like we have a linear combination of atomic orbitals, we also should have the same number of electrons that came from our valence shell of orbitals. So we had 1, 2, 3, 4 atomic orbitals for each oxygen. So I should have 8 in total, which I do. And I should also have 8 molecular orbitals. And as you can see, I have 1, 2, 3, 4, 5, 6, 7, 8. So a linear combination of atomic orbitals makes the number of molecular orbitals. So I've used up 4 of my electrons, 5, 6, 7, 8, 9, 10, 11, 12. So this uses up all 6 valence electrons from each oxygen atom, gives us 12. And this is the correct molecular orbital diagram for oxygen. And importantly, I want you to consider the fact that this actually appears to be a paramagnetic compound. And if you were indeed to place oxygen in a magnet, it would be attracted to that magnet because it is indeed paramagnetic. Additionally, if we were to calculate the bond order, again, it's half the number of bonding electrons, 2, 4, 6, 8, minus the number of anti-bonding electrons, so 2, 4. This would be 8 minus 4 is 4, divided by 2 is a bond order of 2, which matches the diagram, the Lewis dot structure that you would draw if you were to draw O2. So while your Lewis dot structure does indeed match with the bond order, an important thing that the molecular orbital diagram tells you that the Lewis dot structure does not tell you is that this is in fact a paramagnetic substance that contains 2 unpaired electrons. Now notice the difference between these two. Every diatomic molecule that is nitrogen and before, so H2, C2, N2, etc., all of them has the pi bonds that are formed lower in energy than that second sigma bond. But from oxygen and further through the periodic table, all of those homonuclear diatomics look more like oxygen, where you cannot have sp mixing because the energy between the s and the p orbitals are so vast that they'll never mix and overlap and push that sigma bond up. Let us consider one final example, HF, or hydrofluoric acid. If you were to look at that energy diagram depicting the relative energies of the effective nuclear charges of these 2 atoms, you would see that the 2s orbital for fluorine, because it has such a high effective nuclear charge, lies very low in energy. In fact, even though those 2s orbitals have the right shape or geometry to overlap and make a sigma bond, they do not have the correct energy. There's a greater than 13 electron volt difference between those 2 atoms, and for that reason, they are never going to overlap and make a sigma bond. So when that happens, we can just bring over those 2s orbitals because they haven't been stabilized or destabilized by any sort of interaction, and draw the new orbital as a non-bonding orbital. So we actually call those non-bonding. Now we see that the 1s orbital does have the right energy to mix with 2p orbitals. There are 2 of them that cannot create a constructive or deconstructive overlap. In fact, this would be no overlap between a px orbital and an s orbital because there is equal repulsion, repelling and attraction from these 2 different phases. This lies perfectly in the center along the internuclear axis. This is pi symmetric orbital, this is a sigma symmetric orbital, and orbitals that have different symmetry cannot overlap to form bonding molecular orbitals. However, the pz orbital, which points in the direction of the internuclear axis, does have the right symmetry because it is sigma symmetric, because if I rotated along the internuclear axis, I would never have a phase change. Similarly, the s orbital is always sigma symmetric. Now we see that the symmetry does match. The energy is also sufficiently close that they can overlap, and that is what will create our sigma bond. So if you were to draw what that linear combination of atomic orbitals looks like, it would be this, where this would be our sigma bond. Similarly, if they were out of phase and they were added together, this would create our sigma star, or sigma antibonding molecular orbital. So now that we know that we can make bonding and antibonding molecular orbitals here, we will do that. So we'll make our first sigma bond. We have a destabilization for our sigma star. And these other py and px orbitals don't have anything that matches in symmetry on the hydrogen atom to overlap and make any sort of bonding interaction. So for that reason, I will bring over 2 orbitals, and those will also be non-bonding, or NB as I've drawn here. So now we can go in and take our electrons. Well, first let's count the atomic orbitals. We have 1 for the 1s orbital, 4 for the orbitals on fluorine. That should give us 5 molecular orbitals because it's a linear combination. We have 1, 2, 3, 4, 5, so that matches. Now we need to retain the number of valence electrons in our molecular orbital diagram. So we have 2 here, we have 2 here, 2 here, and 2 here. This is going to give us 2, 4, 6, 8. Hydrogen has 1 valence electron. Fluorine has 7 valence electrons because it's a halide. And now I see that that gives us 8 orbitals. Now, importantly, this also matches because we only have 1 bonding orbital filled. The others are non-bonding. Non-bonding orbitals do not come into play when considering bond order. It is only the bonding minus anti-bonding divided by 2. And I see the bond order is 1, which matches my Lewis dot structure for fluorine. Similarly, I see that I have 2, 4, 6 electrons in non-bonding orbitals. And I also have 6 lone pairs, so my Lewis dot structure matches my molecular orbital diagram. Now I want you to take a good look at this molecular orbital diagram. The HOMO is going to be the electrons on fluorine, because they are closest in energy to atomic orbitals on fluorine. That is true for all of the non-bonding orbitals, but the HOMO, or the highest occupied molecular orbital, is that non-bonding electrons found on fluorine. Now, if you look at which orbital is closest in energy to the LUMO, or the lowest occupied molecular orbital, that is actually hydrogen. So hydrogen is closer in energy to this sigma star anti-bonding orbital. And I want you to think about what happens in an acid-base reaction. So in our class, we'll largely focus on the Lewis definition of Lewis acids and bases, where Lewis acid is an electron acceptor and a Lewis base is an electron donor. And you can think of this like OH minus. OH minus has these lone pairs, and when it interacts with an acid like HF, it is donating those electrons. And when it donates those electrons and it comes and abstracts that hydrogen, which becomes a proton, this kicks off the electrons back over to fluorine. And if you remember from organic chemistry, this creates H2O and F minus. So we've retained our charge, and this is basically the reaction that you have probably seen before. Now we can use molecular orbital theory to predict why this interaction actually occurs. So notice that the LUMO, or the lowest unoccupied molecular orbital, is closest in energy to a hydrogen atom. So if we were to draw this LUMO, I would actually draw it. So it is this sigma star, but here I haven't indicated any sort of polarity. However, I have already said that the electron density energy is closest to hydrogen because this sigma star is closer in energy to that proton, or that 1s orbital on hydrogen. So if I were to draw this, I would actually draw, so if hydrogen is here and fluorine is here, then what I would actually draw, if I were to draw this molecular orbital, is there would be a tiny little bit of that p orbital from fluorine, and a really large portion would be from hydrogen, that s orbital. So if I were to, add these two together to create that LUMO, what it would actually look like would be like this. Okay, so I've done a linear combination of these atomic orbitals. This is an anti-bonding orbital because there is a node here between those two atomic orbitals. Along the internuclear axis, if you rotate it, none of the phases change, so this is sigma star. However, what you should notice is that the density is found largest around hydrogen, which is why when it accepts electrons, the orbital that has an empty shell that can actually accept electrons is actually closest in energy to hydrogen. So when OH minus donates those 2 electrons, that is actually what's happening. And notice that if we were to add 2 more electrons here, this changes the bond order. This now places 2 electrons in an antibonding orbital, which changes our bond order to 0. And when that becomes 0, that is actually what causes that covalent bond to break between hydrogen and fluorine, and the electrons will be retained on fluorine. And this is why I think molecular orbital theory is so cool, because not only does it tell us the location of electrons, but if we know those location of electrons, we can start to predict things like reactivity.